In the last lecture, we discussed the first topic of pressure, in which we applied the force balance in x direction, and we came to the conclusion that if any area element of zero dimension is oriented, then the force per unit area from any direction comes out to be same, which we concluded here. If the area element is larger, then the governing equation that we get was this. But as soon as we invoke the condition of limit of delta x delta y tending to 0, means we are uh, doing the analysis at a certain point where the dimensions in x and y is not that significant. We came to the conclusion that pressure in normal direction, pressure in the direction of n is equal to pressure in direction of x, and by applying the force in y direction, we can prove pressure in y direction will also be same. So at any point, the pressure is not dependent on the direction from which it is applied. Okay. The next topic that we discussed about was density, and there we discussed the concept of continuum hypothesis, in which we said that the fluid is not continuous everywhere because it constitutes of several molecules which is having some random motion. And in order to define a differential equation, it is essential for each and every property to define everywhere in the space. But this is not possible in the case of fluid, because certain molecules, due to the randomness, may leave some space and there is no any presence of any property because there is nothing present at any point. So what we did was we defined a control volume whose length scale is not very big, not very small, such that the fluctuations in the property are not that significant, and corresponding to that length scale we defined the control volume, which constitute of several molecules, not one molecule, and that is called fluid particle, which can be repeated throughout the space to get the entire domain. Now the benefit with this control volume we can get with that we have got, which constitute of several molecules, is that we are able to define each and every property throughout the entire space, so that the differential equations are valid everywhere. So this was the thing that we discussed in continuum hypothesis. The next topic was bulk modulus, how Mach number is related with the fractional change in density. The viscosity, discussion about viscosity, in which we discussed how the impact of the plate is seen in y direction. Fluid is flowing in x direction, and due to the presence of plate, the velocity is at the surface of wall becomes equal to 0 by no slip condition, and the impact is continuously forwarded to the upcoming layers. The velocity continuously increases from wall as we go away from the wall, and after reaching a certain distance, the velocity becomes equal to the u infinity, or free stream velocity. Then we derived some concept of derived a equation of tau, how shear stress is directly proportional to strain rate, and how strain rate is related to the velocity gradient. We have taken a special case of the fluid is flowing in x direction and its gradient in y direction. The layer above at a distance of delta y is having a velocity u plus delta u, which is greater than the velocity of the bottom layer. With the help of this illustration, we derived expression of tau is equal to mu into du by dy. Note that this is not the generalized equation. We will discuss the more generalized equation more formally in the upcoming course. The last topic we discussed was kinematic viscosity, the units of kinematic viscosity, and how kinematic viscosity is different from the viscosity that is defined by mu. And what is the significance of mu and rho we discussed. Now, in today's lecture, the first thing that I am going to take is Reynolds number. Reynolds number. Reynolds number is defined as inertia force divided by viscous force. Inertial force divided by viscous force. So what is inertial force? Let us try to have some intuition about inertial force. Suppose flow is flowing in a channel between the two plates in x direction, and we place some obstruction like plate or our hand in between. Due to the flow, whatever flow force is exerted, due to the convection of the flow in x direction, there will be some experience of force by the fluid onto the obstruction that we are placing, is generally kept as inertial force, and the viscous forces are the forces due to the obstruction of, or due to just reduction of velocity of one layer, which is moving slower than comparatively so slower than the layer, which is, suppose I take the example like suppose I have a layer, and above this there is another layer which is moving at a velocity which is greater than the velocity of the bottom layer. So suppose these particles, red particles, are moving at velocity u plus delta u, and the blue particles are moving at a velocity u. So the blue particles will try to get into these red particles, and the red particles will try to enter into the blue particles. And due to the interaction of the molecules between these two layers, which are moving at a different velocity, there will be the blue molecules will try to resist or oppose the motion or decrease the velocity of the red particles or red layer, and the molecules which are moving at higher speed in u plus delta u, the red molecule, when it comes into the blue layer, it will try to reduce the velocity of the blue layer. This is because there will be some force exerted by a layer on the other. This is due to the viscous forces. Okay, so the inertial forces are trying inertia. If suppose we have some kind of flow in a channel, or we have a flow in a channel, and due to the flow in a channel, there will be some Reynolds number associated with it. We will discuss what is the exact formula of Reynolds number, but just try to understand that Reynolds number gives the comparison between inertial forces and the viscous forces. If the inertial forces are significantly higher compared to that of the viscous forces, then the Reynolds number will be high, and if the Reynolds number is smaller, this implies that the viscous forces are more dominant than the inertial forces. Okay, so suppose there is some kind of base flow, or fluid is flowing, and the velocity profile is given by this. And now what we do, we introduce some kind of disturbance at any point. This you can more easily encounter in the example of tap. Suppose we have a tap and fluid is flowing through it, and fluid is passing, and this is the floor. So you might have seen, if you pinch this fluid, again it becomes some kind of chaotic, and after moving some distance it becomes chaotic here, but after moving some distance it will again, after pinching, it will become little bit of chaotic here, but it will again become the same as it was flowing before. So this is the example where viscous forces are dominant. And you might have seen the example, if the flow is flowing very fast, and you pinch some kind of disturbance by using your hand or something, or your finger, you might have seen the flow has become very shaky and very chaotic, and everywhere it splashes out. So this is the example where inertial forces are more dominant. So the tendency of the viscous forces is to distribute or disseminate or distribute the disturbance given at any point. Suppose I have a flow and viscous forces are dominant than inertial forces, then what will happen? When I introduce some kind of perturbation or disturbance, perturbation and disturbance are the synonyms in fluid mechanics. Suppose I introduce some kind of disturbance at any point, then what will happen? If the viscous forces are dominant, it will try to disseminate or distribute the disturbance to the neighboring fluid particles, and because of which the disturbance will not grow at any point, it will die out. So this was the condition that you have seen in figure 1, where the disturbances die out. In the second example, since inertial forces are dominant, inertial forces does not tend to distribute because viscous forces are very less here, the distribution of the perturbation or the disturbance at any point, which we have introduced externally, is not able to get distributed. It continues to build up, and because of that, you have got a very chaotic flow. So, if inertial forces are if viscous forces are very large, if viscous forces are large, this implies that Reynolds number is small. And if, or this implies the stability, because the perturbation will die out, stable flow. And if inertial forces are large, this implies that Reynolds number is large. This implies that unstable flow or chaotic flow. Instability, you will see the disturbances are not dying out, but it is continuously increasing. Okay, so this was the basic concept which was related to the Reynolds number, is comparison between the two different kind of forces, inertial forces and viscous forces. And due to the dominance of one kind of force, you will see some kind of behavior due to the uh, significant effect of the other kind of force. You will see the different kind of behavior which I wanted to discuss here. The next in the next topic, I will try to take one example on the basis of the derivation that I did in the last class. So this derivation is this problem is based on that derivation. Suppose I will take a mass pulley system in which I have attached a mass m1 and mass m2 with a pulley. This is mass m1, this is mass m2, and there is some kind of liquid which is filled in between the table surface and the mass m1, and this mass m2 is kept free and it can move under the influence of gravity. What the information is given in the problem is the gap between this m1 and the table is very narrow gap, and that narrow gap is the gap between the bottom of the mass m1 and the top of surface of the plate is given by height h, and the viscosity of the fluid which is filled is mu. Okay, viscosity, this is the description given. This mass is m2. About a string, it is written that it is inextensible. And about pulley, it is given that this pulley is massless. Okay, you have to find what is the velocity as a function of time for this mass m1. Okay, let us try to solve this problem. So there are different kind of forces which are acting on mass m1, m2 and the pulley. So let us try to draw the free body diagram. Free body diagram of pulley. Let us start with pulley. On pulley we have one string attached like this, the other string is attached like this, and suppose the tension here is T1 and the tension in this string is T2. This is attached to the table. Now since there is no any acceleration, linear acceleration on the pulley as it is attached to the table, only it can rotate around its axis. So what I can say, I need to do the torque balance, not the force balance. Okay, so what will the torque? Summation of all torques is equal to moment of inertia I into alpha. Okay, the first torque is T1 into the radius is, let us say, R. T1 is the tension into R minus T2 into R, because both the forces are torques will be acting in the opposite sense. T1R is trying to rotate it in the others in one direction, and T2R will be trying to rotate it into the different direction. Okay, this is equal to moment of inertia I is given by mass of the pulley into R square by 2. This you can find by in any kind of physics book, that what is the mass, what is the moment of inertia of a circular disc about the center, about the axis passing through the center. That comes out to be mr square divided by 2 into alpha. Sorry, mr square by 2 and alpha is multiplied, which is the angular acceleration. R gets common. T1 minus T2 is equal to mp into r square divided by 2 into alpha. Since mass mp is equal to 0, it is assumed in the problem r into T1 minus T2 comes out to be equal to 0. This implies that T1 is equal to T2. Let us say this is equal to T. This is the first equation. Now let us go on to the mass M2 free body diagram. So on mass M2, how the forces are acting? There are two kinds of forces which can act on a body. Since we are not in electrostatics and all, so there cannot be, that is also a kind of on the, because of the presence of the electric field on charge, some kind of force can be there. But in the field force, the only gravitational force we will be considering, and there can be two kind of forces. The first force is the contact force, and the second force is the field force. So on mass M2, the field force which is acting in the downward direction is m2g. In the top, in the direction above, there is a string attached which will apply a force which will be given by the contact force, and it is the T, because we have proved that T1 is equal to T2 is equal to T from the first equation. So directly I can write T. The let us say the acceleration is occurring in the downward direction is A. So what I can write? This, assuming this direction to be positive and the upper direction to be negative, m2g minus T is equal to m2a. This is the second equation that I can get. The third thing that I can do is apply the mass balance on mass m1. So free body diagram of mass m1, I will apply m1 is the mass. The string is pulling this mass in this direction, so this is tension, and there is one force which will be acting due to the fluid which is kept in between the surface of the block and the table surface. So there will be a force which will be acting, that is equal to the stress tau into area of the base of this particular block. So what is the value of tau? Tau we have derived comes out to be mu into du by dy. Since it is said that the gap is very narrow, it is said that in the problem the gap is very narrow, so du by dy is linear. Velocity gradient in between a very thin height h is given by, suppose the velocity is v, so mu into v by h. Du by dy comes out to be v by h for a very narrow gap. Okay, if the gap has been given very significant, then we would not be able to write this du by dy to be v by h. But since the gap is very narrow, we assume that the velocity gradient is linear. Okay, so v by h we can write. So it is in problem, it is given that the gap between the surface of the table and the mass m1 is very narrow. That's why we are using that particular condition of narrow gap to write du by dy to be equal to v by h. Otherwise it is not always true. Okay, and multiplying this by area will give the force will be given by mu into v by h into the bottom surface area of the mass, which is given by a. Okay, so now let us write this to be positive direction, this to be negative direction, and acceleration is happening in this direction. Okay, now write the balance force. T minus force is mu into V by H into A is equal to m1 into acceleration A. Now what I can say, I can name this equation 3 and since t is also, I can write acceleration is equal to dv by dt. Instantaneous acceleration is given by rate of change of velocity as a function of time. So the instantaneous acceleration I can write as dv by dt. Okay, so what I can write, equation 3 can be written as t minus mu into v by h into a is equal to m1 into dv by dt. Now t I can write in form of from equation 2. I can put this equation 2 in equation 3 to write t as a function of velocity. Okay, or at least acceleration, and acceleration is directly can be written as dv by dt. So from equation 2 I can write t is equal to m2g minus m2a, m2g minus m2a minus mu into v by h into a is equal to m1 into dv by dt. Okay, m2g minus mu into v by h into a comes out to be equal to m1 plus m2 into dv by dt. Note that both the accelerations will be same because in the problem it is given that the string is inextensible. So whatever acceleration we encounter in mass m2, the same amount of acceleration can be seen at mass m1. This is the differential equation we have got. What I can do now, dv divided by, just separation of variable technique we can use to solve this differential equation to get v as a function of time. Okay, so what I can write, dv divided by m2g, m2g is constant, minus mu into v into a divided by h is equal to m1 plus m2 into dt. Okay, this is something we can, sorry, dv is equal to dt divided by m1 plus m2, m1 plus m2. Integrating this equation at time t is equal to 0, velocity was equal to 0. There was no any velocity, both the things were at rest. And at time t is equal to t, there will be some velocity v. So integrating this equation, we will get velocity as a function of time. There is only integration which you can do very easily. This is very simple integration. I'm not going to integrate, but this is the method in which you can get velocity as a function of time. Okay, the next example I will be taking, example 2. In this example I have taken a inner circular cylinder and outer circular cylinder. The center is here, and in between these two cylinders we have filled some kind of fluid or liquid. Okay, some kind of fluid is filled in between, and the radius, outer radius of the outer cylinder, outer radius of the cylinder is given by r2. The inner cylinder radius is given by r1. Okay, and the initial inner cylinder is rotated with angular velocity omega. The outer cylinder remains fixed. The outer cylinder is not rotating. It is rotating across the axis, by the axis, this center of the concentric cylinders. Okay, now what is the amount of power input to shaft of central cylinder for rotating it? Okay, and what is the torque, what is the torque required? These are the two things that we need to calculate. So torque required, I need to calculate. What is the torque required? Solution of this problem is, so if inner cylinder is rotating what you can say, if inner cylinder is rotating, the fluid at the inner cylinder will be having the same velocity as that of the inner cylinder. Suppose this inner cylinder is rotating with angular velocity omega. So what is the velocity at the surface of the inner cylinder? Omega into r1. Okay. Outer cylinder is kept at rest, so the outer cylinder velocity will be 0. The fluid at the inner cylinder, which is just adjacent to the inner cylinder, will have the same velocity as that of the inner cylinder due to the no slip condition. The no slip condition says that if surface is moving at some velocity v, the fluid particles which is adjacent to that surface will also move with the same velocity v. Okay. So because of that, what I can say is the velocity at the inner cylinder will be given by omega into r1, and velocity of the outer cylinder, the fluid which is very adjacent to the outer cylinder, will be given by 0. Now we will take a element of variable radius r and try to see how we can evaluate the torque associated with this. Okay, this is the, suppose this is r and the outer radius is r plus dr, and this means that the thickness of the element that we have taken is given by dr. Okay, so what will be the force which will be required, what will be the torque which will be required? M is equal to, since both the cylinders will have length L, suppose length of the cylinder is L, length is L. So how can I write torque? I can write what is the area, 2 pi RL. This is the area associated with the inner cylinder, into viscosity into, I am writing shear stress. In this bracket I am writing shear stress, mu into du by dr. Mu into du by dr will give, what will be the velocity gradient? Du by dr into mu is the viscosity. This will give this, both the brackets when gets multiplied, it will give force, and it is multiplied by r to get the torque, because r is the length which is drawn from the center of these two cylinders, and r is the length which is perpendicular to both the force and the axis. So this will give the lever arm. So M is given by 2 pi r into L into mu into du by dr, which is the stress, and the 2 pi RL gives the area, this means force, into r, which gives the torque. Now I can integrate this equation. How I can integrate this? Du is equal to M into M divided by 2 pi mu L r square dr. Integration of du is equal to integration of M divided by 2 pi mu into L into r square dr. Velocity is omega r1 at r is equal to capital R1, and velocity at r is equal to capital R2 comes out to be equal to 0. Now integrating is very simple. 0 minus omega r1 is equal to M divided by 2 pi mu into L into minus 1 by r, r1, r2. It is given by M divided by 2 pi mu into L into 1 by r1 minus 1 by r2. This is equal to minus omega r1. So M is given by 2 pi mu into L into omega r1 divided by 1 by r2 minus 1 by r1. This is equal to 2 pi mu into L into omega into r1 square r2 divided by r1 minus r2. Okay, so M comes out to be equal to this. Okay, this is the total amount of torque which is required to run the two cylinders, in which the inner cylinder is rotating at omega r1 and the outer cylinder is kept at rest. Due to the relative motion between the two different layers, there will be some kind of shear stress that will be acting, and to overcome that shear stress we apply the torque which is driven from the axis, center axis, which is given by, let us say, O. So what is the total amount of stress that is need to what is the total amount of torque which is required is given, is calculated by this formula, by integrating this formula, and we will get the value of m2 be equal to 2 pi mu l omega r1 square r2 divided by r1 minus r2. Note that the force that we need to apply, or the torque we need to apply, is due to the fact, due to the stresses acting, and the velocity gradient is different. At r is equal to r1 you have highest velocity, and the shear stress will be different at r is equal to r1. As you increase from r is equal to r1 to r is equal to r2, there will be variation of the shear stress, and correspondingly you will have to apply the torque for every layer to rotate, because the velocity gradient will be different. Okay, so in order to do that, we have taken an element, and we have assumed that du mu into du by dr is the total shear stress for that particular element, and we have integrated this particular equation from r1 to r2, keeping the correct limits. Okay, the next example that I'm going to discuss is a kind of a surface which is kept at the bottom. This is the surface. This is the surface. And a piston like structure is kept at this, and about the center about this axis this piston is rotating. Okay, so if this piston is of circular shape and it is rotating with some angular speed omega, and this height is h, so what is the relative velocity between the piston surface and this surface is kept at velocity 0? This is at rest. This is suppose this is a and this is a prime. So a is at rest, a prime will be having some velocity because of the piston like structure, circular piston like structure is rotating at some angular velocity omega. So there will be some velocity at a prime and there will be zero velocity at a. Similarly, if I write b prime and b, there will be the different velocity difference between b prime and b, because it is at a larger radius situated. This is r2, this is r1. Similarly, at point c prime and c, there will be different velocity difference, and there will be d prime and d, there will be different velocity difference. And note that it is circular, so if I will take a circular element. Okay, so at a distance r, suppose I take differential distance dr. Okay, and that dr runs over the entire circle, a thin strip of circle. Suppose I am taking. So force, what is the force which is acting on this element that I have taken? I have taken this kind of element because it is circular. I have taken this kind of element at a distance r from the center, or r plus dr is the outer radius, r plus dr. Okay, so what is the force? Force on thin element at radius r. This can be given by, what is the total shear stress will be acting? U into omega r divided by h. Here the as I, this is the radius, at radius r we have a thickness dr. So this dr element will be moving at a velocity omega into r. This will be moving at a velocity omega into r, and this is at 0. So what is the velocity gradient you will be taking? Omega r minus 0 divided by h. So that I have written as mu into omega r divided by h, into what will the area associated? Area associated will be, area is this area, this area. What will be the area associated with this? The area associated with this will be 2 pi r dr. 2 pi r dr. Okay, 2 pi r dr. And this is the total amount of force. This is the total amount of force which will be acting on the thin strip or thin element. So what will be the total amount of torque which will be associated with this? Df into r. So dm is equal to mu into omega r divided by h into 2 pi r dr into r. So mu omega into 2 pi by h into r cube dr. dm is equal to 2 pi mu omega divided by h, integration of this from r is equal to 0 to r is equal to capital R, and here the velocity dm will be equal to 0, and here dm will be equal to m. At r is equal to capital R, total torque will be there, so r cube into dr. So m comes out to be equal to 2 pi mu omega by h into r power 4 by 4, and again m comes out to be pi mu omega r to the power 4 divided by 2h. This is the total amount of torque associated with this. Here you have to keep it in mind that the force which is exerted at the lower radius, which is closer from the, I will take a circular element. This thing you need to be very careful because it is not looking like that. It is on the plane surface we have drawn this figure, but the circular strip that we have taken, if we have to take a circle which is at a closure radius from the axis, suppose this is the axis, and we will take a circle which is having a less radius. In that case, the angular velocity is the same, but the velocity associated at point A prime will be lesser. And if I go at a radius which is larger, suppose at a B prime, then the velocity of this point, because angular velocity is same, at B prime the velocity will be greater. So the difference in velocity between A prime and A is smaller. So because of that less velocity gradient, the stress mu into du by dr will be less at the nearby locations, and the stress will be higher at the locations which are away from the center, away from the axis. So because of that, we have taken an element and we have integrated it from 0 to r. Okay. Now these are the two problems that I wanted to discuss. After this, I want to come to the next topic, which is surface tension. Okay. So let us try to discuss surface tension, which is a very important phenomenon in fluid mechanics. Surface tension. So surface tension is something which is associated with interface. Suppose this is water and this is air. So suppose I have any molecule which is placed at this location in bulk water. So what will happen? This bulk water molecule is surrounded by same kind of water molecule from all the sides. So the interaction that this center water molecule will experience from all the different directions will be very uniform. There will be no any non-uniformity associated with the forces acting from all the different directions. But in the same case, if I move on to surface, suppose a water molecule is placed at the surface, it will encounter some kind of interaction from the bottom, because there is some water molecule which is present below it, and at the top it will have some different kind of air molecules of air which may contain oxygen, nitrogen, hydrogen, anything. So the interaction will be very different from the top and very different from the bottom, because it is exposed to the different ambient. It is not exposed to the water molecules from all the sides as it was the case with the first molecule. So there will be net inward force which will be acting due to the water molecules. The force which will be exerted by the molecules from the top is not equal to the force from the bottom, so there will be a net inward force which will be acted on this molecule on the surface. So technically, if you will think, then the surface would not be stable, because any molecule which reaches the surface, there will be imbalance of the force from the top and the bottom, and it should continuously come down to the bulk, and whatever molecule comes at the surface, it will have to come down to the bulk. But this doesn't happen. You see that various fluids, the surface seems to be stable. Why does this happen? So there must be some kind of energy associated with surface. Energy associated with surface. And due to this energy, even due to the force which is applied, the imbalance of the force which is applied from the bottom, due to the same kind of molecules present, the imbalance of force is countered by the total energy which is available with the surface. And this energy per unit area is given by surface tension. Energy per unit area is given by surface tension. So this is something which I wanted to explain, the basic phenomena associated with the surface tension. Okay, surface tension is also defined by force per unit length. Suppose I have any interface of water and I have put a thread in between. So what is the force applied on this particular thread which I have kept? And force applied per unit length, what is the length of this thread, is also given by surface tension. Energy associated per unit area or force applied per unit length, both the things will give the surface tension. Okay, now let us say that I have a solid and there is a droplet which is kept on this solid. This is liquid, this is solid, and this is vapor. So let us say that the surface tension is acting on the tangent to the surface. So this is the surface of liquid, and vapor is exposed from outside. This side is vapor. So if I draw tangent to liquid and vapor, this is associated with as LV, or surface tension is associated with liquid and vapor. The similar fashion, this line if I draw, it is tangent to both liquid and solid. So I can write SLS, liquid and, or let us say sigma LV, and this is sigma LS. Okay, sigma LS. Now if I draw this line, then it is given by sigma, this is tangent to surface and vapor, so it is given by sigma SV. Now if I want to balance the force in x direction, so what I can write, sigma L sigma, suppose this angle is theta. Theta is the angle which is made by this droplet with that of the surface. Okay, this angle is given by theta. So if I want to balance the force, balance surface tension force, what I can say, sigma SV is equal to sigma LV cos theta plus sigma LS. So from here cos theta comes out to be equal to sigma SV minus sigma LS divided by sigma LV. This is the equation which is called as Young's equation. Okay. Now let us move on to the next topic, and we would like to correlate how the surface tension is related to that of the pressure difference. Okay, so we want to show the relation between how surface tension is can be related to that of the pressure difference. Okay, so suppose I have a surface A, B, C, D. I have taken this surface from part of any body, and this is the surface A, B, C, D. The radius of curvature of the surface of AB is given by R1 and CD is given by R1. So the radius of curvature of AB and CD is same, which is given by R1. The radius of curvature of BC and AD is same, which is given by R2. So I can write it here. R1 is radius of curvature of AB, CD. All right, and R2 is radius of curvature of AD or BC. AD or BC. Okay, so this is something which we have seen, and suppose now what we do is we extend this surface. We want to pull this surface, and whatever ABCD was present, it has now come it has now become A prime, B prime, C prime and D prime. ABCD is enlarged to form A prime, B prime, C prime and D prime. Now the radius of curvature associated with A prime, B prime and C prime, D prime is now changed from R1 to R1 plus delta Z. Okay, and the length associated with the radius of curvature associated with BC and AD will now be R2 plus delta Z something, which we can say the radius of curvature associated with AB and CD is given by R1 initially, and after extension for A prime, B prime, C prime, D prime, for A prime, B prime, which is equal to radius of curvature of A prime, B prime is equal to radius of curvature of C prime, D prime is given by R1 plus delta Z. Okay, x and x plus delta x are the arc length associated with AB and A prime, B prime. Okay, and the arc length associated with CD and C prime, D prime is given by BC is given by y, and B prime, C prime is given by y plus delta y. The same AB and CD is given by same arc length x and x plus delta x in A prime, B prime and AB. Similarly in CD and C prime, D prime also we can say the arc length is given by x and x plus delta x. Okay, so by similarity of these two surfaces, I can write that R1 divided by R1 is given for ABCD divided by R1 plus delta Z, which is associated with A prime, B prime, C prime, D prime, is equal to x divided by x plus delta x. R1 is the radius of curvature associated with ABCD, and R1 plus delta Z is radius of curvature associated with A prime, B prime, C prime, D prime. Okay, now the arc length associated with AB is given by x, and arc length associated with A prime, B prime is x plus delta x. Now the similar proportion can be written as R1 plus delta Z divided by R1 is equal to x plus delta x divided by x. Subtracting 1 from both gives delta Z by R1 is equal to delta x by x. Similarly, you can write it for R2, and this is one equation, and delta Z by R2 will come out to be delta y by y. Okay, this is the second equation. We'll use these equations later. Now let us say due to extension of the surface ABCD, delta P is the pressure difference associated with the surface. So what is the work done? Work done by delta P. So delta P is the pressure difference. What is the force associated with delta P? Delta P into x into y. And what is the displacement, which is equal to delta Z. This is the work done by delta P. I will write this as equation 1. What is the work done by surface tension? Work done by surface tension is the difference in energy associated with A prime, B prime, C prime, D prime, and ABCD. A prime, B prime, C prime, D prime, the larger area is having some energy associated with it, and the smaller area will have some energy associated with it. So the difference is given by the total amount of work done. Okay, so what I can say, sigma into area is x plus delta x into y plus delta y minus xy. This is the total change in the surface energy associated with these two. Okay, so what I can say, sigma into xy plus x delta y plus y delta x plus delta x delta y minus xy. This minus xy plus xy gets cancelled. Sigma is equal to sigma into x delta y plus y delta x. This what will we give? This will give by the total amount of work done by surface tension. Work done by surface tension. Then these two work done should be same. So we will equate the work done by delta P and work done by the surface tension will come out to be delta P into x into y into delta z is equal to sigma into x delta y plus y delta x. Not we will divide the whole equation by delta xy. Delta P into delta z is equal to sigma into delta y by y plus delta x by x. And delta y by y from the equation 1 can be given as sigma into delta z by delta x by x is given by delta z by r1, delta y by y is given by delta z by r2. So delta p comes out to be equal to sigma into 1 by r1 plus 1 by r2. This is the final equation. Okay, so how sigma is related to delta p is given by this relation. Now one thing we have to keep in mind, that if we will take the surface ABCD from any sphere, then all the radius of curvature should be same, because we are taking it from the sphere. So in that case r1 will be equal to r2. For generalized case where r1 and r2 are not same, delta p is related to sigma by this fashion of sigma into 1 by r1 plus 1 by r2. Okay, for spherical droplet, for spherical drops or droplets, r1 is equal to r2. This implies that r1 is equal to r2 is equal to r. This implies that delta p is equal to sigma 2 sigma by r. Okay, for the bubbles we have two surfaces associated with it. Bubbles have two surfaces. This implies that delta p is equal to 4 sigma by r, because for one surface I have seen, for the two surfaces, this is the structure of the bubble. So for the two surfaces, this is the first, this is the second, we will say delta p is equal to 4 sigma by r. Okay, this is something we obtain. Now we will study rise of liquid in a column. If I have certain liquid kept in a container, this is the last topic. I think after this we will be diving more into the fluid statics and more conceptual things. These are the very basic topics that we need to cover, so we are covering this. This is the last topic. After this we will enter into the fluid statics, which will bring more interest, because these are all topics of high school physics. So let us just for recapitulation do this. This is the capillary and sorry, there will be, we can see that there will be a rise due to, if I will put this particular tube in there, liquid which is kept in the beaker. Okay, so what is the physics behind it? We will draw the surface. This is the surface, and at this surface sigma is acting in this direction, which is acting as in the direction tangent. Okay, the angle from the vertical is given by theta. Angle from vertical is given by theta, and there will be pressure from both the sides. Let us say this pressure is Pg and this pressure is PL. Okay, we have obtained just that the delta P is related to the surface tension as sigma into 1 by R1 plus 1 by R2. 1 by R1 plus 1 by R2. And for our case, which we are discussing here, rise of liquid in column, R1 is equal to R2. Okay, so delta P comes out to be equal to 2 sigma by R. But the R that we have taken here, the R we have taken here is the radius of this particular spherical, this is something sphere, and its radius is given by this capital R. But what we want to write this particular expression in terms of the radius of the capillary. Okay, the radius of the tube that we have kept inside the liquid. So we want to write in that form. Suppose this is the complete sphere which we can draw, and something like this. This is the radius R, and this is the radius small r, and this is the capillary. Okay, here this is the direction of sigma, and from vertical it is making some angle theta. Okay, so if this angle is theta, then this angle will also be equal to theta. Cos theta will be equal to small r by capital R. So capital R can be written as small r by cos theta. So here I can replace delta P is equal to 2 sigma divided by R divided by cos theta. Delta P expression comes out to be equal to this. Now whatever height which is associated with this will be given by delta P is the, let us say this is equation 1. Delta P is the pressure difference across point 1 and 2. Cross point 1 and 2. Suppose this is point 1 and this is point 2. Suppose this is point 3. So what is the difference of pressure between point 1 and point 2? Pressure at point 1 is given by P atm, and suppose pressure is point 2 is P2. Pressure at point 3 is also equal to P atm, as it is also exposed to the atmosphere. So if we want to calculate the pressure difference P1 minus P2, I can say the P1 minus P2 becomes equal to P3 minus P2. Okay, and P3 minus P2 is located at a height, P2 is located at a height h above 0.3, and the density of the fluid is rho, height is h, and acceleration due to gravity is g. So the difference between P1 and P2 can be written as equal to P3 minus P2, and it comes out to be rho gh. Okay, so replacing in the place of delta P, I can write rho gh is equal to 2 sigma cos theta divided by r, and h comes out to be equal to 2 sigma cos theta divided by rho gr. The point to be noticed here is r is the radius of pipe or capillary. Capillary tube. One more point you need to take care here. If r is very high, this implies that you can see that height is direct inversely proportional to r. If r is very high, this implies that h will be very low. H is very low. So if the pipe radius will be very small, the height up to which the liquid column will rise will be more significant. If the radius or diameter of the capillary that we are taking is very large, in that case the height up to which it rises, the liquid rises, is very less or less significant. Similarly, I can write, suppose I will take example of mercury and liquid. In that case, the liquid does not rise but it falls, and in that case I can write, suppose this is mercury Hg, and our capillaries, and this is water, then it will be so something like this. And the tangent, if I will draw from here, this angle is given by 180 minus theta. So the formula here comes out to be delta P is equal to 2 sigma cos of 180 minus theta divided by r. And again for delta P I can write h bracket में rho hg minus rho water into g is equal to 2 sigma cos of 180 minus theta divided by r. From here I can find h, the value of h. Okay. So this is all that I wanted to discuss. From the next class onwards, we will start the fluid statics, and this is the last topic that I wanted to discuss today. From the next class we will discuss fluid statics. Okay. Thank you.